We're going to start our discussion of number theory with some basic ideas that I'm sure you're already familiar with, but we're going to do it in a more precise way that we'll be able to use to prove other things. And it's going to give us an opportunity to start our discussion of mathematical proofs where most mathematics starts, with some definitions. So to start, we're going to look at what it means for a number to be odd versus even. Now, I'm sure you're familiar with kind of the verbal definition, right? A number is even if it's divisible by 2 and odd if it isn't. But we're going to need something more precise like the definitions I've got here. So we're going to say that a number is even if and only if it can be written as 2 times another integer k, and it's odd if and only if it can be written as 2 times another integer k plus 1. Now, what I really want you to notice here is that both of these definitions use the if and only if connective, right? Every definition is going to follow this format. A new term, if and only if, then what the new term means. Now, with that said, remember what we saw earlier when we were discussing biconditionals. P if and only if Q is equivalent to if P then Q and if Q then P. Now, this is important because it's telling us that a definition actually gives us 2 pieces of information, right? Looking at our definition of an even number, this is saying first that if a number is even, then it can be written as 2k for some integer k, and it's saying the converse. It's saying if a number can be written 2 times k for some integer k, then the number is even. So as a practical matter, we're going to use both of these versions just in different contexts. So I've got an example here for us to look at that illustrates how the definition works. Right? What I want to do is I want to show that 12 is an even number. And to do this, I'm going to use the second form that we got from the previous discussion of what a definition means, right? That's the one that says if a number can be written as 2 to the k. And I'm going to write over here on the right-hand side, right? So I'm going to go down to the next line. Leave a little space over there on the right if you're taking notes here. So if a number can be written as 2 to the k for some integer k, then it's even. Right now, in this case, right, we want to talk about 12. So I'm going to say n equals 12, and if I take k equal to 6, then yes, 12 is equal to 2 times 6. So the k that the definition talks about does exist for 12, right? And what's my conclusion? Therefore, 12 is even. Now, okay, that was pretty trivial, right? But what I really want you to focus on is the reasoning that went on behind it. And hopefully that looks a little familiar based on your understanding of valid argument forms. If we replace there exists an integer n, excuse me, if there exists an integer k such that the number can be written 2k. If we replace that with p of x, and if we replace its even with q of x, and now down here, right, what do I do next? I said if n equals 12, so for n equals 12, p of n is true, right? I showed it here when I found this particular k, right? Therefore, q of n is true, right? So what I have here, what my argument is just a specific example of universal instantiation, which we know is a valid argument form. Right, so in the last lecture, right, we saw an example of how the transitivity form could be used to prove a specific number was a solution to an algebraic equation. And here we have an example of how universal instantiation can be used to prove that a specific number is even. Right, so now, as a practical matter, yes, you would never explicitly cite universal instantiation as a reason in a proof. It's kind of like when you go into a house, your attention is all on the door, not the door frame, right? Even though the frame is what's holding up the door, okay, and making it possible for it to work properly. So, in the last example, we saw how to use the Q implies P reading of the definition of an even number. So how about the P implies Q version, right? That's the if a number is even, right? I already know that I'm looking at an even number. If a number is even, then it can be written in the form 2k for some integer k. Right, we're going to use this version of definitions repeatedly when we start trying to prove things. Right now, I don't want to get too deep into actually trying to prove something at this point, but I've got a theorem here that we're going to look at in more detail later in the section that will illustrate how this form of a definition is used. Right, the proof gives us a statement about even numbers. Okay, so my first step here would be to say, by definition, there exists an integer k such that a is equal to 2k. Then I would say the same thing for b, right? And continue from there to look at their sum and work my way to a conclusion. So what we've seen here and in the previous lecture are really our first examples of proofs. Now, they're relatively simple proofs, really just a single step, each based on one valid argument form, but yeah, they still qualify. Now, in the next lecture in this series, we're going to take this a step further, right, with some proofs that build on our new definitions of odd and even, but that require a few more steps to get to their conclusions.